All right, the plan for today is to wrap some things up in chapter 3 and then start chapter 4. First, I want to consider the case of what happens when there's repeated eigenvalues, and there's two main things to do, one of which is kind of typical and one of which is kind of atypical in that situation. We'll consider the trace-determinant plane again, families of linear differential equations. You'll have a graded problem or two actually over the weekend related to that, so we'll think about that. Think briefly about three-dimensional linear systems. That's the end of chapter 3, and then start chapter 4 talking about what are called forced harmonic oscillators, where there's some sort of external force involved. What happens when there's a repeated eigenvalue? That's kind of tricky, actually. Here are a couple examples with repeated eigenvalues. I'll go ahead and enter this first one there. Let's start to think about what would happen if we were just doing this by hand with this first example here. So the matrix A is 2, 1, -1, and 4. And the first thing I want you to notice with this matrix is there's no way to tell ahead of time that there's going to be a repeated eigenvalue. There's no obvious way to tell just looking at that. What's the determinant of A minus lambda I? Let's see what we get. Multiply those, you'll get 8 minus 6 lambda plus lambda squared. Subtract the products of the off-diagonal elements, we'll be subtracting a -1. So the characteristic polynomial simplifies to lambda squared minus 6 lambda plus 9, which can be factored. In fact, it's a perfect square. It's lambda minus 3 quantity squared. So that means there's only one eigenvalue. Why don't you close the door? Thanks. Lambda equals 3. However, because it's got a square there, we call it a repeated eigenvalue, or an eigenvalue of multiplicity 2. It's repeated, well, I'll say repeated, but sometimes you'll hear people say it has multiplicity 2. Well, okay. What happens if we go ahead and try to find a corresponding eigenvector? So lambda equals 3. Again, my quick technique here is to look at the first row of the A minus lambda I, make those coefficients of x and y, and set it equal to 0. When you plug in the eigenvalue, lambda equals 3 in this case, so we get 2 minus 3 is -1. Negative x plus 1 times y equals 0. In general, eigenvalues, vectors, are going to be non-zero vectors where the x and y components satisfy that equation. In other words, they're equal to each other. So, for example, 1, 1 is going to be an eigenvector. However, we need two linearly independent eigenvectors if we're going to write down a general solution in the usual way. We only have one. Any non-zero multiple of this is another eigenvector for this eigenvalue, but it would be a multiple. It would not be linearly independent from this one. So it seems like we run into a problem as far as finding the general solution. I could say that e to the 3t times 1, 1, that function is a solution. And in fact, any constant times it is a solution. In fact, it's a straight line solution. But there's no other straight line solutions. I mean, all straight line solutions are on a single line is what I should really say there. The line going through the origin and the point 1, 1. The eigenvalue is positive, so evidently it's some kind of source, at least in that direction. The origin is the only equilibrium point. 0 is not an eigenvalue. The determinant of this matrix is non-zero. So the origin is the only equilibrium point, but we only have one line that has straight line solutions on it. Now I could certainly use StreamPlot. Maybe I should quick to see what the rest of the solutions look like. You know, is it really going to be a source if it's only a source in one direction? StreamPlot, A dot, x comma y. See what it looks like. There it is. The origin in the middle. You you should draw a big dot there. That would be the equilibrium point. It does look like a source in all directions. I could certainly draw nullclines. If all I was after, if I didn't have the technology there, I could certainly draw nullclines to help me draw the rest of the phase portrait and think about signs of dx dt and dy dt. The nullclines in this case would be 2x plus y equals 0. In other words, the line y equals negative 2x would be the x nullcline, looking at that first row. Looking at the second row, the y nullcline would be negative x plus 4y equals 0. In other words, y equals 1/4 x. The x nullcline looks about like this. The y nullcline looks about like that. X nullcline is where you cross vertically. Y nullcline is where you cross horizontally. And then again, if you check the signs of dx dt and dy dt, you should get ultimately that kind of picture. Solutions are looking like that picture. You can check that. Evidently, some solutions go down here before they cross there and then head back up that way. You can get a pretty good picture without finding a formula for the general solution. You can see the behavior of solutions. But what if you wanted a formula? What if you needed a formula for something? Well, it turns out the best guess to make, and this is not by any means obvious, is to guess the following as the general solution, although it's not going to be in a usual kind of form. I'm going to go ahead and take, well, take e to the 3t and multiply it by my initial condition vector. That's an arbitrary initial condition vector. Little x0, little y0. I've used that notation before, plenty of times. That function, as it stands, is a solution only if y0 is an eigenvector, only if y0 is a non-zero multiple of v or the zero vector. That would be a solution. It would be the equilibrium solution of the origin. If y0 is a non-zero vector that's not an eigenvector, not parallel to that one, then this is actually not a solution because there are no other straight line solutions. However, it turns out to be part of the general solution if you add another term. And the term we're going to add is a little tricky. It's a little bit of guesswork, essentially. T times e to the 3t times, actually, I'm going to go ahead and call it v. V, it's going to turn out, will be an eigenvector, a non-zero multiple of that, though you wouldn't know that necessarily ahead of time in guessing this. Go back to not circling this. Well, I only have that one circled, so I'll leave that. This will turn out to be we will see an eigenvector if y0 is not an eigenvector. And it'll actually equal the zero vector if y0 is an eigenvector. And it will equal the zero vector if y0 is an eigenvector. Very strange. I'm just telling you what's going to happen here without explaining why. Okay. You also have this extra t in there. I haven't really talked about these kinds of cases before. It's been in your reading. If you've done your reading, adding an extra factor of t here should seem somewhat familiar, even going back to chapter 1 in guessing particular solutions that are, if you don't put the t there, they'd be multiples of solutions, general solutions of corresponding homogeneous equations when we were considering non-homogeneous equations. So it's been in the reading. I haven't talked about it in class. And there's no intuition about for sure why this is going to work. But it will work. Certainly that function satisfies the initial condition. Plug in t equals 0. The second expression here will be 0, the 0 vector. That'll be 1 times y0. It certainly satisfies the initial condition. What's less clear is that it satisfies the differential equation. What kind of condition on v, and maybe its relationship to y0, would make it satisfy the differential equation? Well, the left-hand side, when you substitute, find y prime by the chain rule and the product rule, actually, is going to give you 3 to the 3t y0. Chain rule for the first term. The second term, I need the product rule. Differentiate the t and get 1. 1 times e to the 3t times v. Plus, differentiate e to the 3t, get an extra factor of 3. Product rule. I'm going to make a mistake.
Do you need a t-square set, or is it just t?
Right here? It should be just t, right?
Well, there's a t already on the outside, and you just did it with the e to the 3t.
Yeah. I mean, I used the product rule on this?
Yeah. So
Derivative
your left
1.
side already has t is 1. So then on the right side, you need it to be t times 3t. Because you did the product on the right side.
No, I think this is right.
Yeah, I think it's right.
Yeah, it's right.
You sure?
Yep.
Okay.
Yep.
Yeah, because you're going to get the t times the derivative of e to the 3t, which will just involve an extra factor of 3. Yeah, I think this is right. The right-hand side is going to be a times y of p. Multiply this on the left by a. Distribute the a through. Factor out scalars. Let's see. We'll get this. These are the only two terms in both that involve that extra factor of t. So they're going to be equal if and only if, it's the abbreviation for if and only if, IFF, not an actual word. If and only if AV equals 3V, and if and only if V is an eigenvector for the eigenvalue 3, or V could be the 0 vector as well, and this would be true, which is going to take care of that case. What kind of condition would make these things equal? You can cancel the e to the 3t's. The condition would be ay0 equals 3y0 plus v, which if you solve it for v is equivalent to v equaling a minus 3 times the identity matrix times y0. And again, this is not obvious, but it's going to turn out that if y0 is an eigenvector, actually it should be clear if y0 is an eigenvector that this will be, v will be 0. That goes back to the original definition of eigenvectors. If y0 is not an eigenvector, which is going to be the typical case, it's going to turn out that v will be an eigenvector. And so, since I meant to use that as an eigenvector, I meant to use that as 1, 1 actually here. What I found for the eigenvector, that's valid. I haven't proved that. I haven't proved that if y0 is not an eigenvector, that v will be. It's actually based on the fact that lambda is repeated. You need that fact to prove that. But we'll just accept that as true. Okay? This discussion is in the book in section 3.5. It's something you should have actually read about already. I'm not going to make a big deal out of this. It's not going to be on the test, actually. I should never say that during class, should I? Oh well. I think it's worthwhile to show you. It is, in the trace-determinant plane, the boundary between spiraling and non-spiraling. Call the trace-determinant plane here for families of linear systems. You've got the three critical loci, the t-axis where d is 0, where the determinant is 0, the positive d-axis where d is positive, and the trace is 0, and this repeated root parabola, we typically call it, d as a function of t is 1/4 t squared. And it's along that repeated root parabola where you have repeated roots, where your eigenvalue is just have, in 2 by 2 cases, what we're talking about here, where you have one repeated eigenvalue. Usually when you have one repeated eigenvalue, I guess I can do the other case, usually you have only one line of straight line solutions. You only have one eigenvector that's linearly independent by itself. There are not two linearly independent eigenvectors. However, there are special cases, diagonal matrices in particular, it's really the only special case actually, where your repeated eigenvalue is the number on the diagonal, if they're equal to each other, which I've made them equal. And in that case, actually, every single non-zero vector in the entire plane is an eigenvector. The entire plane consists of straight line solutions. For that kind of example. And in this case, the origin is a sinc. So if you get a diagonal matrix where the entries in the main diagonal are equal, that number in the main diagonal will be the eigenvalue and it will be repeated. And actually, every non-zero vector in the entire plane will be an eigenvector. Every solution is a straight line solution except for the origin. Okay? I would encourage you to try the algebra of that on your own. That's the simpler case, actually. But yeah, come back to the trace-determinant plane now again. Let's consider more examples. I'm actually going to help you with 2 of your completion problems. It's going to be at least 2 graded. 2 graded problems, maybe even a 3rd graded problem during the weekend, which are going to be kind of complicated ones. They're going to be involved. So I want to give you help with them. This is one of them, where your matrix capital A equals what you see there. It's a function of little a. Little a is the parameter. This corresponds to a family of differential equations. dy dt equals little a square root of 1 minus a little a squared, negative 1, 0 times y. Of course, that corresponds to a family of systems of scalar equations too. dx dt equals ax plus that times little y. dy dt equals negative x. It's a family. One system for each value of a, although a here actually can't be anything. We don't want imaginary coefficients in our matrix, complex coefficients, or imaginary. We do deal with, of course, imaginary and complex numbers in here, but we don't want them in the matrix itself. So we don't want a negative number under the square root. We want 1 minus a squared to be greater than or equal to 0, which is equivalent to a squared being less than or equal to 1, which is equivalent to a itself being between negative 1 and 1. That's the range of values for the parameter that we want. Are there any bifurcations that occur along in there? That's what we're after here. The quick method is to calculate the trace and determinant as functions of the parameter. can use that kind of notation. The trace is a plus 0, which is just a. The determinant is a times 0 minus negative 1 times square root of 1 minus a squared, which simplifies to square root of 1 minus a squared. To help you understand the relation to the trace determinant plane here now is you want to graph this parametric curve, where a is the parameter. Parametric curve, as I always mean with parametric curves, a curve in a plane that's traced out as the parameter varies. In multivariable calculus, we almost always have the parameter be time here, and I suppose you certainly could imagine that a is time, if you want, just for the sake of imagination. You've got to graph that parametric curve. You can graph that actually pretty easily without technology by thinking about it. D here, since it's square root of 1 minus a squared, and since t is a, no matter what a is, we always satisfy that equation, which I hope you remember has got a graph that's a upper half of a semicircle, of a circle called the semicircle, the upper semicircle, for the unit circle, in fact. You square both sides. That's the equation for the unit circle in the TD plane. Since we're taking the positive square root, we get the upper half of it. As little a varies from negative 1 to 1, the curve we trace out is going to look like that. Pretend that's a semicircle. Not drawn perfectly. Anytime it crosses one of the critical loci, we're going to think like analysts, not topologists. We've got a bifurcation. So there's at least 3 bifurcations. Should I count these two things as being bifurcations? I suppose you could. I mean, a can't really cross negative 1 because it can't be less than negative 1. And it can't really cross positive 1 because it can't be greater than positive 1. But I suppose if you really wanted to, you could say there's a bifurcation at those 2 points as well. This one certainly corresponds to a equals negative 1 because t equals a. This one corresponds to a equals positive 1. This one corresponds certainly to a equals 0, right? T equals a. So we cross the d-axis when t is 0, which means when a is 0. The only little bit of work you have to do is finding these 2 points in terms of when the curve crosses it, what values of a lead to the curve crossing those. And it's just a matter of doing some algebra. Replace d with d of a, replace t with t of a. I'll write the equation like this. You essentially have to solve that equation for a. T again is simple, that's just a. D is a bit more complicated, it's square root of 1 minus a squared. I'm going to get a 4th degree equation when we square this. Hopefully everything's okay. Square both sides, get 16 minus 16a squared equals a to the 4th. Even though it's a 4th degree equation, it's quadratic in a squared. I could use the quadratic formula if I need to here. Is this light enough over here? Maybe I should go over there. Let's go over here to the lights on.
Okay.
A to the 4th plus 16a squared minus 16. Hoping I'm not making a mistake here. Does it look okay to everybody?
I'm not saying.
Use the quadratic formula now. A squared will be negative 16 plus or minus square root of 16 squared is what, 256? Minus 4 times 1 times negative 16 is plus 64. Negative 8 plus or minus, we're only going to want the plus one actually, because a needs to be real. I'll leave the plus or minus there for the moment. 64 plus 256 is 320. We want the plus 1, and it will be positive, because square root of 320 over 2 is going to be bigger than 8, right? Yeah, square root of 320 is bigger than 16. A is going to be plus or minus square root of negative 8 plus square root of 320 over 2. That can be simplified, I'm sure, here. 320 is, what, 80 times 4, which is the same as 16 times 20. We thought it was 64 times something, I think here. 64 times 4, no.
5.
5? Is that right? Yeah. Yep. 64 times 5, 64 is a perfect square. Square root is 8. 8 divided by 2 is 4. Looks like, if I haven't made a mistake, that we get that. Does that look good? Those are your two other bifurcation values. And of course, you can approximate. How do the bifurcations occur? You go from here, where 0 is an eigenvalue, and so you're going to have infinitely many equilibrium points. In here, you're going to have a non-spiral sink. In here, it's a spiral sink. On the boundary, it's a repeated eigenvalue case. You've got one straight line solution, probably. Here, you're going to have a center. Here, you're going to have a spiral source. There's another repeated eigenvalue with probably one straight line of straight line solutions. Here's a non-spiral source, a real source. You never have a saddle point. You never go down below the t-axis. You can see if this is what's really happening by animating it. Not sure what happened there.
A to go from -1 to 1.
Yeah, that's it. Thank you. That was the danger of copy and paste in that case. Yeah, A is -1, 0 is an eigenvalue. You've got infinitely many equilibrium points. Hopefully you can tell they're on, looks like they're on the y-axis there. All the equilibrium points are on the y-axis. The eigenvectors for the eigenvalue 0 are going to be vertical. As A increases slowly, let's slow this down here. Not quite so fast. All right, we'll watch the whole thing. Starting over again when we get to the end there. We get a non-spiral sink, then it's a spiral sink, and then it's a center briefly, right about now. Then it's a source, spiral source, then it becomes a non-spiral source eventually. Okay, and then your behavior repeats itself. That's actually going to be one of your completion problems. So I've worked it through for you. Not completion, graded. You need to explain things. I talked about the math. Another one of your graded problems is going to involve two parameters, just like you had a completion problem for today that involved two parameters. Now the trace and determinant depend on both A and B. This example is that's a two-parameter family of systems that's sort of doubly infinite in a sense. Don't overinterpret that. A and B can be in anything. There's no restrictions on them. What's the trace and what's the determinant? This time they're functions of both A and B. I'm using notation a bit here. Not a big deal. The trace is going to be A plus 1. The determinant is going to be A minus B. How How do you deal with this? As A and B vary, we don't get a curve. I mean, if we fixed B or A and let the other one vary, we'd get a curve, a parametric curve. But A and B, we want to be anything, and to vary independently of each other. Turns out the best thing to do in this kind of situation is to sort of redraw the parameter plane to not be a TD plane, but instead be an AB plane. And again, you have this completion problem the other day. For today, actually, that was similar to this. So this shouldn't be completely foreign to you. But what do you draw on the AB plane? You want to draw the corresponding critical loci. What does D equals 0 correspond to? D equals 0 corresponds to, based on these equations, A equaling B, or B equaling A. In other words, the line with the slope of 1 to the origin is a critical locus in the AB plane corresponding to the t-axis critical locus in the TD plane. Since this is where you have 0 eigenvalue, 0 as an eigenvalue, in the AB plane, this is where you're going to have 0 as an eigenvalue. When A and B are equal, 0 will be an eigenvalue. You'll have infinitely many equilibrium points. Which isn't surprising when you think about it. When A and B are equal, these two rows are going to be multiples of each other. How about the positive d-axis? D greater than 0, t equals 0. What does that correspond to? Well, t equals 0 corresponds to A equaling -1, because t is A plus 1. D positive means A minus B is greater than 0, which is perhaps best thought of as saying B is less than A. So, if you draw a line A equals -1, which is a vertical line over here, but also make sure you keep B less than A, so you're below this line, that gives you another critical locus in this new AB plane. It corresponds to the positive d-axis in this one. That was where you got centers. So when A and B are on this line, that's where this system is going to have a center. When A is -1 and B is less than -1, -2, -3, whatever, you're going to get a center. What about the repeated root parabola? Think of this equation as 4d equals t squared. I got to write that now in terms of A and B. Not trying to solve that equation for A and B, because A and B vary independently of each other, but I'm trying to get a relationship between A and B for when 4d equals t squared. D is A minus B, T is A plus 1. If that relationship holds between A and B, will be on the repeated root parabola in the TD plane. The system will have a repeated eigenvalue, and probably just one line that consists of straight line solutions. Yeah, it won't be a diagonal matrix because of the one up here. So definitely you only have one line of straight line solutions. Might be nice to simplify this a bit. Maybe solve for B as a function of A. Put the 4B on the other side, bring everything else over to the left side, and then switch the sides. Maybe you're going to get plus 2A minus 1, I think. I put the 4B on the right, put everything else on the left. And then switch the sides. So b is going to be 1/4, negative 1/4 a squared, plus 1/2 a minus 1/4. If you graph that, either with your calculator or using calculus to figure out max and min, or well, the max in this case, because it's a parabola opening downward, it actually is going to go through the same point right here, which should make sense because these three meet at the origin. That's the point that corresponds to the origin. It's not going to have a max there, I don't believe. You can do a quick derivative calculation to see the max is going to be it. The derivative of that with respect to a will be negative 1/2 a plus 1/2. That'll be 0 when a is 1. So when a is 1 is when we have a max. Does it go above the a-axis? Plug in equals 1 there. Looks like it just touches the a-axis when a is 1. So it looks like it looks something like that. Now, we're not done, but I'm not going to go anymore. I'll just say you should finish this off, besides doing the writing, by saying in which situations do you get saddles, sinks, non-spiral sinks, non-spiral sources, spiral sinks, spiral sources, centers. I've already said some of those. It should be somewhat clear what the possibilities are. Like probably up here you're going to have saddle points. Probably in here you're going to have spirals, whether they're sinks or sources, and on which side of that line is not so clear. You should test certain values to help you figure it out. Certain values of A and B. Does that make sense? Pick values in each region for A and B to test in the matrix and figure out the eigenvalues to help you classify. It might be the way to go about that without to make the fewest mistakes at least. All right. Three-dimensional systems is going to be something, here I go again, not on the test, but I want to inform you about them. I suppose I could put them on the test, but I have to give you help. There's a 3x3 matrix. In the 3x3 case, you'd really want to consider your capital Y to be a three-dimensional vector whose components are little x, little y, and little z. And dy dt, d capital Y dt would be dx dt, d little y dt, dz dt. And your right-hand sides for this example, I could put this on the test. Maybe I take that back. I'll talk about how I'd have to give you help. The right-hand sides would be negative 3x minus y minus z, 4x plus 2y plus 5z, negative 2x minus 2y minus 5z. The thing I'd have to give you help with is the calculations of, for example, the determinants, because I haven't told you how to calculate a 3x3 determinant, and I'm not going to. Those of you in linear algebra know how. Even if you haven't had linear algebra, you might know how. The determinant here is non-zero. That means this matrix is non-singular, invertible, which means the origin in three-dimensional space is the only equilibrium point. The phase space is going to be three-dimensional. X, Y, Z. What's the characteristic polynomial? It turns out to be a cubic. A minus lambda I. I is now the 3x3 identity matrix. This turns out to be a cubic. Finding roots of cubics is always possible, though it can be difficult. Though in this case, the roots are pretty easy. I'd have to give you an easy example. Or just tell you what the roots are. Negative 3, negative 2, negative 1 are the roots. You can check those by plugging them in there. Those are the three roots. Those are the three eigenvalues. You can find corresponding eigenvectors by setting up systems of equations. And in Mathematica, you can just use eigensystem. Three eigenvalues are negative 3, negative 2, negative 1. These are corresponding eigenvectors. This one, or any non-zero multiple of it, is an eigenvector for negative 3. This one, or any non-zero multiple of it, is an eigenvector for negative 2. And this one, or any non-zero multiple of it, is an eigenvector from -1. Are these three vectors, which we would write as columns, by the way, are they linearly independent? That's harder to tell. They're not multiples of each other, but that's not enough to prove that they're linearly independent. Actually, the fact that this determinant of the original matrix is non-zero is enough to prove that they are linearly independent. And in fact, you can also think of that in terms of the eigenvalues. The eigenvalues being distinct, actually, is enough to also prove that these are linearly independent. If you take an arbitrary linear combination of them, but it would involve three vectors, times e to the lambda t in front times a k, corresponding k in front, you would get the general solution. I'm going fast. Probably before I put this on Moodle, I'll type some of that out. You can use the matrix exponential again to write the solution for initial value problems very compactly. Okay, that's the benefit of the matrix exponential, by the way. I don't know if that's been clear. I did try to emphasize that before. The matrix exponential is beneficial, especially when you've got technology, because it allows you to write the general solution, in this case, without having to use dsolve, for example, or dsolve value. Pretty quickly we can write the general solution in terms of the initial conditions here, not doing it in terms of the k's, doing it in terms of the initial conditions. You can do the flow. It's got the same formula, except we use x, y, and z instead of x0, y0, z0. You want to think of this in terms of t being fixed, and think of this as a linear function of x, y, and z. But then it's a family of functions. For each t, you get a different function. And you can think about how sets get mapped under the flow, and we will here in just a second. What about the nullclines? Now you've got three nullclines, an x nullcline, a y nullcline, and a z nullcline. Where that's 0, that's 0, and that's 0. And those end up being planes in 3 dimensions instead of lines. We're relying a lot on technology here. Don't worry about it too much. I want you to get the basic idea. Oh, wow, look at that. 3-dimensional picture. What do we got going on here? Those 3 planes you see are the nullclines. I don't remember offhand which one's the x, which one's the y, which one's the z. The blue curve is a solution curve. I can change the initial condition to move that around. It's going outside of the box there, by the way. It didn't break into 2 disjoint pieces. It's just not inside the box. The entire time here. The eigenvalues were all negative. The origin is a sink. Those solution curves are heading toward the origin as t goes to infinity. The orangish lines, those are straight line solutions. There's 3 linearly independent ones. They're almost in the plane. It's like they're almost linearly dependent. They're almost in the same plane. They're not actually, but they almost are here, if you look at those carefully. And what's the green sphere for? That's for the flow. That's my oil spill in 3-dimensional fluid now. The fact that the origin is a sink is going to mean, as time goes by, that sphere gets shrunk to an ellipsoid that heads toward the origin. Okay? So you can do all these kinds of things in 3 dimensions and use Mathematica to try to visualize it. That's a very quick summary of that I want to get across today, at least. You should read section 3.8 to try to get a fuller understanding, and especially about the general solution. I guess I am saying it's possible I could have you find general solutions. Though I'd give you help, I'd tell you what the eigenvalues are, I'd tell you what the eigenvectors are. Save some time and save something for work. So you should read that section and know how to do that. Are these flows just for fun? Just for fun visualizations? No, I will say they're for more than that. And when we get to chapter 5, we'll see that another benefit of the flow perspective is it allows us to define certain kinds of things very nicely in a way that would not be so easy if we didn't have the flow concept. So we will see it's more than just for visualizations. All right, last 5 minutes, I want to get started on chapter 4. That's what your completion assignment is going to include, for the most part. Forced harmonic oscillators. We're going to consider two main examples, exponential forcing and sinusoidal forcing. What's the simple harmonic oscillator equation? We've talked about that plenty, right? Y double prime plus py prime plus qy equals 0. Having something non-zero on the right makes this non-homogeneous, makes it forced. And in fact, you certainly can think of this thing as a force being applied to your mass on your spring. If you solve this equation for y double prime, meaning you solve for a on one side, and then multiply it through by the mass, m times that would be an external force that would be applied to the mass of the spring. Now it's hard to imagine how would you apply an exponential external force. That might be hard to imagine, but we will try to imagine it anyway. This is a sinusoidal forcing. That's maybe a little easier to imagine. It could, for example, correspond to maybe having the mass on a table, and then you oscillate the table itself back and forth, which makes the external force be sinusoidal and related to gravity. You can actually move the table back and forth like that. So that's a little easier to imagine. But the first case is easier to solve. Let's do an example. The sinusoidal case, it's trickier to solve. We'll end up using complex numbers again. We'll see as a beneficial way to think about the sinusoidal case. Let's do a particular example. Let's go y double prime plus, let's go 8y prime plus 15, making the eigenvalues nice and simple. -3 and -5. Should be able to do that in your head. Think about the corresponding quadratic equation in S. Can be factored. And by the way, that's the same as the characteristic polynomial you get in the matrix form. I hope you noticed. I think I mentioned that once before. The eigenvalues are going to be -3 and -5. Nice. What kind of forcing function should we pick on the right? Let's pick, say, negative e to the negative 60.
Is that supposed to be 15y?
Yes, thank you. Thanks for catching that. That's a big mistake on my part. Common mistake, because you're thinking sort of along those lines, but don't make that mistake I just made. Thanks for catching that. So what do? It's very analogous to what we've done before with non-homogeneous equations. Consider the corresponding or associated homogeneous equation. The general solution of that in scalar form I'm going to call YH is little k1 e to the -3t plus little k2 e to the -5t. Right? Because the eigenvalues are -3, -5. I'm writing the scalar form, not bothering to go to the vector form. And then you guess a particular solution to the non-homogeneous. What should you guess? If you think about it, it's an educated guess. It probably should be something related to that. E to the -6t, some constant times e to the -6t. And you've got to solve for the constant. That hopefully works. Find the derivative. Find the second derivative. Plug those things into the left-hand side. See if I can do this in my head. You're going to get 36a minus 48a. 8 times 6 is -12a plus 15. 3a? Looks like we're going to get 3a e to the -6 needs to equal e to the -6t. That'll happen if a is 1/3. If I haven't made a mistake, that looks like it's going to work. People were nodding, it sounded like I did it right. And then, your general solution of the original non-homogeneous equation is the sum yh plus yp. That thing plus this thing when a is 1/3. And you can use it to solve initial value problems when you have two initial conditions for the position and the velocity. Okay, so very similar, pretty easy. That's why I felt like I could do it in 5 minutes. And I guess I succeeded. Well, I went 6 minutes. Okay. It's Friday. See you on Monday. Have a good weekend.